Hello, class. I thought that I would start this next lecture. I seem to be getting back into the lecture things. In fact, I happen to have 3 other lectures. The past lecture on RC first response circuit analysis went on for a bit longer than I thought. It went on for about 45 minutes, but what I did in that RC lectures, I looked at both things. I looked at the source free as well as the step response. And I got those both done in one lecture. And I think that's even going to be easier to do with the RL first order circuit. And that's what I'm going to analysis, because that's what I'm going to look at here. And I think that you can guess that it's probably on the same order, because we always say that when we have a DC source and it's hitched up to a resistor and in line with a capacitor, right? That, and I'll just put the ground over here, that it starts as a short circuit, right? So a capacitor starts as a short circuit. And what would that say? That would say that if when it starts, the voltage across here, right, is going to be 0 volts. So we would think that the voltage for the capacitor is going to be 0 volts when it starts, right, at 0. Right, 0 volts across there at 0. We would still have some type of voltage drop across the resistor, and that resistor would be its maximum voltage drop, right? So the voltage drop across the resistor here, that would be V sub R. We want to look at that too, the voltage across the resistor, voltage across the capacitor. So the capacitor starts as a short circuit. So we would think that this then would really equal to 0. So it starts at 0 volts, and then as it charges, it goes up to, whatever the V sub S. Let's call this V sub S. And so it eventually gets up to V sub S, right? Now, with when I'm doing the same, now that's, of course, charging. Now, let me put that there. Charging, it starts as a short circuit, and then it goes to an open circuit, right? So we would see that the voltage across the capacitor here starts at 0 and goes up to V sub S. What's the voltage across the resistor? The voltage across the resistor goes from V sub S, and then it goes down to 0. So if we were looking at the voltage across the resistor up here, we would see the voltage across the resistor start up here and then go down like this, right? Does everyone see how that's working? And of course, this would be exponential, and this would be to the e to the minus x, and this would be 1 minus e to the minus x. In fact, so that's what we've really got. In fact, why don't we look at those two, right? If we were looking at e to the minus x, we would see a function that looks like this. And if we're looking at 1 minus e to the minus x, I happen to have a new pen here, we would be looking at something like this, wouldn't we? So this is 1 minus e to the minus x. And the one down on the bottom is just going to be e to the minus x, right? So y equals e to the minus x, y equals 1 minus e to the minus x, right? And so those are the two different types of charging, discharging, and they work for the inductor as well as they work for the capacitor. And that's what I'm here today to do. So I'm here to look at the RL circuit. So if we had that circuit again, where I drew, but instead of having a capacitor there, I'm just going to put a line here again. That's number 1. And then number 2 is over here, and that's just going down to the bottom, to the ground. And then we've got some other wiper that we can go from 1 to 2 here, right? So that then is going to go through a resistor, just like it did the last time, and then an inductor. Right, so we've got a resistor and we've got an inductor in series. And then this is just going to be V sub S. And so when I charge an inductor, we're going to look instead of at the, like this is for our voltage, right? So we're really looking at, voltage over here for the capacitor, the voltage across the capacitor, or we could look at the, voltage across the resistor, whatever, but we're going to draw. Later on, we're going to look at how these change. What I really want to do now, though, is I want to derive the discharge of an inductor. Let's say that I charge this inductor up. I swing that over to 1, and I charge it up, and then I swing it to 2, right? So after I've charged it up, I'm going to swing it to 2 and have this circuit right here, so that I would have the inductor then discharging, through the resistor. Whereas in the beginning, I'm just going to have the, let me get a green pen because I like to use green for go. We would just have something like this, right? And that would be going to fill up the inductor. I'll just continue that around. All right, so that's what we want to look at. When we're discharging that inductor, what are we really doing? And let's look at this circuit now, just the red circuit right here. I'm going around in a circuit, right? So I know that if I'm going around in the circuit and I'm discharging the inductor, and that's going through the resistor and continually going around, what do I have there as far as the KVL goes? Right? So what I have is I know that my voltage across the inductor must equal my voltage across, well, actually I should, because they're going to be opposite. The voltage of the inductor plus the voltage of the resistor, because one is opposite to the other, is going to equal 0, right? That's what KVL tells us. And so if I look at that then, and I look at the voltage across the inductor, I've got LDI dt. And then when I look at the voltage across the resistor, that's just going to be V equals IR, so that's just going to be I times R. And I know that that has to equal 0, right? So if I take L out of both of those two sides, let me just use some little arrows here. I like to use the double back arrows. I'm going to divide both by L. So I get DI over DT plus I R over L equals 0. All right. Now let's throw one of those on the other side. I don't really have to do that, but I can do it. And then I end up getting DI over DT equals minus I times R over L, right? Let's switch those around. So now I get DI over I equals minus DT times R over L, right? Now let's integrate both of those. That's just 0 to t, just like it was before. But now what we want to do is we want to integrate this one from whatever that original current was, right? We've got current that's flowing around in here, and that current is I sub O. So we're going to go from I sub O up to I of T. And by I of T, that's the current that's flowing through the inductor. Well, of course, the current flowing through the inductor is the same current that's flowing through the resistor. So that's fine, right? So let's integrate that then. So what we really get then is we've got I, that's the natural log of I, di over I is the natural log of I. And then I want to integrate or evaluate that. So I've got the natural log of, I'm going to put it in here, I sub L of T, I should probably make that a bracket, minus I sub 0, right? No, wait, have I got that right? Yep, natural log of I sub 0 minus natural, yep, that's right, equals R over L times minus T, or minus R over L times T. All right. Now let's take the exponential of both of those two sides, and so what I would get is I sub L of T minus I sub 0 is going to equal E to the minus R over L. I'm going to keep that separate, times T. Because what is R over L, right? R over L equals our time constant. I might take a third lecture here to discuss all of the voltages and the currents and everything that are going on all through here. But right now, what I'm just trying to do is just derive this to show you that it's basically going to be E to the minus T over tau. Wait a second, I got that's supposed to be on bottom. I'm sorry. L over R. I had that backwards. So really what I'm writing here is E to the minus T over tau. And so, of course, I should have done that part. Of course, tau equals L over R because it's in the denominator, right? It's in the denominator. So that's in the denominator, L over R. Why did I put R over L? I don't know. So your time constant is L over R for this thing charging. Or I'm discharging. So we're discharging, but when we're looking at it discharging. So why don't I finish this? So I of L of T, the current that's through the inductor and the resistor, is going to be, I should have got that minus, that should have been, I should have done that before. That should have been I of L over I0. You guys, it's getting late. You got to stop me here sometimes. So I could have done it one of two ways, but no, I couldn't. That would have been the natural log of I of T minus the natural log. Yeah, this should have had a natural log in front of it. That should not be there. There should be minus a natural log there. So this should read, I'm going to put it down here, natural log of I sub L of T minus the natural log of I sub 0. Excuse me. And that should be there, and then that I sub 0 should be under here because as you know, the natural log of A minus the natural log of B equals the natural log of A over B, and that's what we've got right there. And so that's why I had the natural log of I of L of T over I sub 0. And that's what we have. That I sub 0 then would come up into the other side. And so we get I sub L of t equals I0 e to the minus t over tau, where tau is equal to L over R. All right. So when we're seeing the thing discharge, as far as the current goes, now remember, this is not the voltage anymore like we did for the capacitor. This is the current. The current would start out at I sub 0, right? Because it starts as an open circuit and then goes to a closed circuit. And the current would fall off like this, right? Because this is I sub 0 e to the minus t over L over R, right? See how I did that? And then that being in the denominator, L over R would really be R over L. See what I'm saying? So that's what we've got there, and that's what we've got here. Now, for this to charge, it goes exactly the opposite way. And I don't know if I have to go through that whole thing all over again. In fact, what I would rather do is I would rather look at the current and the voltage in these different circuits that we're going to look at to give you a conceptual understanding of what is really going on. All right, let me just look at that right now. Yeah. So let's say that I have these circuits like I'm talking about here, where well, this circuit right here, except instead of having an inductor, I would have a capacitor. And instead of having the, well, I could talk about the inductor right now. So let's say that I'm charging the inductor. This is my inductor circuit. We'll look at that first. All right. Now, an inductor starts as an open circuit. So if I was to look at the voltage, let's just get a couple circuits here. Let's say that I was to look at the voltage across an inductor that is uncharged, right? The inductor is uncharged. So, and then I want to charge that inductor. Well, what does an inductor start out like, right? An inductor starts, so the capacitor, this is my inductor circuit. The inductor circuit, the inductor starts as an open circuit and it goes to a short circuit, just exactly the opposite of a capacitor. So I think you see what's going to happen is, as I'm charging an inductor circuit, here's how the current goes. The current is going to start up here, right, at I sub 0, and the current is going to fall off over a period of time. Okay, so that is the current. It starts at I sub 0 and it falls off. What about the voltage, right, for an inductor circuit? Well, the voltage across the inductor, right, this is the current. The current starts as a maximum. And does that, so what does the voltage across the inductor look like? Well, let's do that. So this is going to be the current through the inductor charging, right? Hey, wait a second. No, that's not right. Like the current, no, that would be discharging that would be discharging. Yeah, I got that backwards. But well, let's look at the discharging side of it. So discharging, I think I started with discharging anyway, because that's the derivation that I'm doing. Okay, so let's look at an inductor circuit. So I through discharging. As I start to discharge the inductor, it's going to start as a short circuit. Let's just put those up there. So when it's discharging, it's already all the way charged, right? So now it's an open circuit. Wait a second, when it's discharging, it's gonna, yeah, no, that's right. My current is going to go down to 0. It's discharging now. Yeah, that's right. Well, I should draw, you know what I should do? I should draw the charging and discharging circuit through here. Let's say that we are putting something like a step function, through here like this, right? If we put a step function through here like this, what we're going to see is we're going to see the charging and discharging aspect of the inductor or the capacitor. So let's just draw a charging and discharging thing. I won't follow that, of course, but if I was to charge an inductor and I was looking at the current in the inductor. So this is the current through the inductor, the charging and discharging. So it would look like this. I'd charge, and then I would discharge. And then I would charge, and then I would discharge, right? So we've got two different phases. Forget these up there. I just wanted to show you what a step function was like. But this is going to be the charging phase. That would be the phase where the V of S is like this, right? Then it would be the discharging phase where I'd be down here at 0. Then I would go back up to the charging phase. Then I would go to the discharging phase. You see the step function that I've drawn over the top of that in red? So that shows where the voltage, the DC voltage is. Call it 10 volts, right? And 0 volts if you want. 10 volts, 0 volts. And let's see how that goes. Now this is my current through the inductor. Yeah, then that's just confusing. So I'm charging the inductor, and then I'm discharging the inductor. So this would be my current. I want to put that there. The current that is going through the inductor. I start at 0, and then I charge it up, right? And what's happening is this starts out as an open circuit. Starts as an open circuit. So how much, if this is an open circuit, let's just take that out of there. Is there any current flowing through that circuit if that's an open circuit? I think everybody sees that there's no current flowing through it. And so the current then is going to be 0. But after a while, that thing becomes a short circuit, doesn't it? So then all of the current is flowing through that circuit, as much current as we could get. It's a short circuit. In fact, how much current is flowing through there? The current that we have right here, that current, maximum current, right, is going to be V sub S over R. Does everyone see that? So the maximum current flowing through the inductor and the resistor is going to be I max V sub S over R if we go all the way to past 5 time constants. And then how's the current going to go? Well, if I stop, if I was to take that right out of there right now by swinging this pendulum over to 2, then I'm going to start discharging just like I showed over here, and we're going to have the current slowly dissipate down too. And if that's long enough, if that's over 5 or 6 time constants, then it's going to go very close to 0, and we're going to start all over again. Does everyone see how that works? Now, the black is the current in the inductor, and it's the current in the resistor. Now, what's the voltage? Right? What is the voltage? And for that, I'm going to use a green pen, maybe. Yes, here's a green pen. Okay, now you can see that we start up at 10 volts, right? So the voltage, the black is that. So the voltage is going to be in green. The voltage across the inductor, that is not a very good green. Let's see if I can get another one. Yeah, I got one. Okay, so the voltage across the inductor, right, is going to be in green. So I would start at 10 volts because doesn't the inductor start, if it's got nothing in it, it's not charged in any way, doesn't it start as an open circuit? That's right. So if it's an open circuit, right, just take it out of the circuit. What would the voltage be? Well, the voltage on top here at that resistor, because it doesn't, the circuit's not closed, would just be V sub S. And then on the bottom, well, it's ground. So the voltage across there is going to be 10 volts. It's going to start at 10 volts, then it's going to go down to nothing, right? Because this starts as an open circuit and finishes as a short circuit, right? And so the voltage is going to go down to nothing, just like this. Is that? No, I think that's correct. Let me just yeah, because it starts off as V and it's charging, and then it gets down to a open right, and then when it starts to go down, so I'm at 0 volts because that's a short circuit. Then I switch it to the other one. This starts to discharge, so it's going to go up like this, right? And then at the end, it's going to be back at V sub S. And then we're just going to continue doing that again and again. So the green, like I say, is V sub L, the voltage across the inductor, and the black is the current across the inductor, right? Now, if we were looking at that, well, I should probably write that in there. So this is the voltage across the inductor. And I think I put I sub L on there already, although it doesn't look like it's very good. I'll just write it over here. So I sub L is the black, and then V sub L is that. And of course, V sub L at the very top here, the maximum, right? The maximum V sub L is going to be equal to V sub S, the source voltage. All right. Now that is for an inductor, which is what we're talking about today, the analysis that we're talking about. And each one of those, by the way, again, this is e to the minus x, or minus t over tau. And then the other one, the green one that we've got up here, is, God, I have to write that. I could write it over here too. That's going to be 1 minus e to the minus x. And that's that one that goes up the other way. So that's how they work. Now you're probably saying, hey, is it exactly the opposite for the capacitor? So let's draw that circuit down here where we're doing the capacitor too, right? So I'm just going to draw the circuit similar to this one that I have over here, and just like I had it the last time, and 1 and 2, and that goes down to ground. And I've got a wiper that goes between those two, and that then goes into a resistor and a capacitor. So that's the same circuit that we have over here. And what I want to show, you know, is this is V sub L and this is I sub L. So what we want to do is we want to show the same thing. In fact, I'll draw it right here. Same as that one. I want to show the same thing over a period of time. And in fact, why don't I draw that same waveform, right? So we're going to see the voltage source like this, then the voltage source off, then the voltage source back on, then the voltage source off again, right? So we've got a step function there. And how and say that it's the same magnitude as we used last time. Let's say that this is 10 volts up here and that this is 10 volts here. So, you know, we know V sub S is 10 volts. Let's just say V sub S. In fact, I'll actually write it there. V sub S equals 10 volts, and that's what we've got. And we're switching that DC on and off, on and off. I don't know, let's say every minute or whatever. It would have to correspond to that. Now, think about this. Let's say think about this, when I first start charging, it's uncharged. So what is a capacitor when it first starts having current flow through it when it's first charging? Isn't it a short circuit? So what would my voltage be across that capacitor if it's a short circuit? Well, I think everybody can see that the voltage is going to be 0, right? So the voltage starts out at 0, and again, then it goes up and it charges. So this is going to be V sub C. Doesn't look very much like V sub L, does it? That's V sub L. V sub L starts and comes down like that. Oh God, did I screw that up? Whereas V sub C, since it starts as a short circuit and ends as an open circuit, V sub C looks like that. Well, if V sub C looks like that, what does V sub L look like? I have no idea where my pen went, but I'm going with this one. So V sub L comes down like this. That's what this comes down like. It comes down like that. You see how they're reversed? And this would be I sub C. So I sub C goes like that, and then when it goes back down here, this is a V sub C. Now V sub C, the voltage across that eventually is going to get up to V sub S, right? That's its maximum. V sub C max equals V sub S. And then when I bring that back down to 0 again, well, obviously the voltage is going to go from that open circuit back down to a short circuit, isn't it? Right? So again, that is my V sub C. And then it's going to charge up again, like that. I didn't draw that very well, but again, V sub C, that's my voltage. And it's just exactly the opposite of V sub L, isn't it? And if I wanted to look at how I sub C, well, this thing is going to go from an open circuit now back up to a short circuit, isn't it? And then it's going to go back down to an open circuit. So you can see that I sub C is exactly the opposite of I sub L. And V sub C is exactly the opposite of V sub L as I ramp these to charge and to discharge. And of course, the reason for that is that we're storing everything in an electric field for a capacitor, and we're storing everything in a magnetic field for an inductor, right? And so that's why they act exactly the opposite to one another. And I wanted to bring that out too. So that's really both of those two functions. As a matter of fact, I'm finding out that I'm just about at time anyway. I was a little better on this one. I think I've kept this to around 36 minutes, but that is not only your source-free RL circuit, but this is also how these things respond to that step response, right? Charging, discharging, charging, discharging. Same with both of them, but they're exactly the opposite. Voltage and current are interchanged when I run a square wave or an impulse wave across charge and discharge a capacitor. Does everyone see that? Whoa, there's the timer too. So I think I may not even be there because I think I started that a little bit early, but that's it. And what I want to do now is I want to start looking. I'll probably have one more lecture on a second order response out of chapter 8, but I want to take 2 lectures anyway to discuss AC and prepare you guys for AC network theory, which is what you're going to see in a very short period of time, and get you sort of up to speed on reactance and impedance, because impedance is not resistance. Impedance is resistance plus J reactance. And you've got to think about that too. Reactance all of a sudden comes in and plays as big a part as the resistance really played in, this. And you're just starting to see how these things react. But how they react to time varying functions is much more important. Okay? So that's great. All right, I'm going to end it right there. And I'll probably, like I say, I might do a short lecture on second order response. But really, it's much more important to get your AC network theory introduction out of the way. I might work on that more so than putting the second order one together. That's not as important as right now. That's really for active, circuits and stuff anyway. Okay. See you in the next lecture.